So our topic for this video is transpositional symmetry. Term might be a little bit confusing, but usually what it means. So when we talk about transpositional symmetry, we talk about sets that maintain the same pitch classes under certain transpositions. So let's say we take a very simple set, which is just a tritone, C, F sharp, and we transpose it by 6. What do we get? We get F sharp, C. That's very simple to see that we have the same pitch classes 0 and 6, and we got the same pitch classes 0 and 6. After transposition, we can see it also in arithmetic terms. T6 of 0 and 6 is 0 plus 6, and 6 plus 6, that's 6 and 12, which is again 0 and 6 on 12. So, and with Music 21, if we if we define the set with 0 and 6, and not with the note names like we did here, you'll see that even the software just automatically transposes it by 6 and keeps it in the same octave. So they're expressed as pitch classes. So this is called transpositional symmetry. And what we want to investigate is which sets have this property, that there are certain ends for which Tn maps the set onto itself. And what we're going to find out is that once again the interval vector plays a big role in determining whether a set has this property and at what transpositions it has this property. You noticed here that the interval vector is 0, 0, 0, 0, 0, 1. It's very simple because there's only one interval here and it's 6. And if you remember that when we have 1 here, that means that we're going to have 2 common tones under transposition. And in this case, because the set only has 2 pitch classes, that means all the pitch classes will be common tones. So the thing we want to look for in the interval vector is that the number of common tones under the transposition is equal to the number of tones or the number of pitch classes in the set. If the number of common tones under transposition, in the case here 2, is equal to the number of pitch classes in the set, obviously this transposition will map this set onto itself. We can make a little for loop here. This is going to take I and go from 0 up to 6. Remember, 7 here is the number of times it's going to do it. So it's going to start from 0, and it will transpose the set 0, and 6, this set, the tritone. It will plot it as 0, 6, and then as 1, 7, 2, 8, etc. And we'll see also on the clock phase what this looks like. So we start with our original tritone here, 0, 6. And then when we transpose it once, we get 1, 7. We transpose it twice, we get 2, 8. We transpose it 3 times by 3, we get 3, 9. We transpose it by 4, we get 4, 10. By 5, we get 5, 11. And we transpose it by 6, we get 6, 0, which is again the same as 0, 6. And just like we saw with the common tones, the role of each pitch class in the dyad switched place. So we started from 0, 6 and we ended at 6, 0. But since a set is an unordered collection of pitch classes, it doesn't matter. It maps onto itself. So again, this is the visual way to see this. And you can see that if we started, for example, with 1, 7, not with 0, 6, we'll get the same result. We start from 1, 7. If we transpose it by 1, by 2, by 3, by 4, by 5, and by 6, we end up with 1, 7 as well. So the property of the tritone, the set of the tritone, that it transposes onto itself under T6, that property of transpositional symmetry is preserved regardless of which tritone we start with.